Hey everyone, welcome back to our next thing in notes. This is lesson 3.4, and we're going to skip around a little bit, but we have some theorems that deal with perpendicular lines. First off, some vocab here. Distance from a point to a line. If you want to find the distance from a point to a line, you find the distance of the perpendicular line. All right, we want to find the distance of the perpendicular line. The shortest distance from a point to a line is where it's perpendicular to it. So for example, if I drew here and I have point P, and then I have point A, and I have point B, and then I have point C here. If I want to find the distance from P to line, we'll call this line M. I would want to measure the distance of the perpendicular. Okay. And we know what a perpendicular well, I can't say that. We know a bisector on this next one. A bisector cuts two things in half. A perpendicular bisector means a line that's or a segment that's perpendicular to another segment. And when it crosses at the midpoint and bisects that segment into two congruent smaller segments. All right, so if I want to draw a picture for that, it would sort of like me having, here's a segment, and here's a segment, and my perpendicular bisector is going to make two congruent segments. Now, let's talk about some theorems today. The first one is called the linear pair perpendicular theorem. This states if we have a linear pair and they are congruent angles, then those lines are perpendicular to each other. So we can use this to prove that two lines are perpendicular. The next theorem is our perpendicular transversal theorem that says, hey, if we have two lines that are perpendicular to each other, and it just so happens that one of those lines is parallel to another, then that perpendicular line is going to be perpendicular to the other parallel line. So I'll read it how it says. It says, if a transversal, so line J, is perpendicular to one of two parallel lines, then it is perpendicular to the other. So this allows us to help prove two things being perpendicular. Oh, excuse me. And then we have our lines perpendicular to a transversal theorem that says if two lines are perpendicular to the same line, then they are parallel to each other. If we wanted to go through a proof, eventually we can go with definition of perpendicular means these are right angles. Definition of right angles mean these are 90 degrees. And now I have corresponding angles converse theorem that then says lines M and N are parallel to each other. Boom. That's how you would prove this. But theorems have already been proven. There's just shortcuts, so you don't have to write all those steps. But the big takeaway here is this lets us prove two lines being parallel. So let's look at, I'm just going to do one of these. It says find the distance from point A to line BC. And again, I want to measure the perpendicular. So I want to measure the perpendicular line. So if I look at number one, A, and the perpendicular is D, I want to use the points -3, 0, and -1, -2. And I want to use my distance formula. It says, hey, I'm going to subtract my X values from each other and then add the difference of my Y values together, and those are squared. And let's get a little distance formula. So I'm going to fill in what I have for my distance formula. I'm going to have, let's say, -1 minus a -3, so that's +3 squared, plus, then I'm going to have -2 minus 0 squared. That gives me 2 square roots of 2, also known as roughly 2.83. So approximately 2.83. So there's two different answers that we could have here. I'm not going to do the other three, but that's the process. We use our distance formula. You just have to identify that perpendicular and find your two endpoints and use the distance formula, which we have done in previous lessons. Now, let's look at the stuff we just talked about today. We want to determine if lines, if any, are parallel, and if so, what's our reasoning? So if I look at number 5 here, I see this intersection is a perpendicular, but I know nothing about this intersection. So I can't prove parallel unless I know that I have two perpendiculars on the same transversal. So I'm going to say not enough information. Let's look at number 6. If I look at number 6, I have two perpendiculars on the same transversal. So I know that if I have a perpendicular here and a perpendicular here on the same transversal, which is R, the theorem said that P and Q are parallel to each other. The reasoning would be our lines perpendicular to a transversal theorem. I'm going to abbreviate that. Number 7, which lines are parallel, if any? I see a transversal here, M, that has two perpendiculars. So I know lines J and K, J is parallel to K, again, because the lines perpendicular to a transversal theorem. Then I also see that I have a perpendicular here and a perpendicular here on line K. So K is the transversal for lines M and N. So M is parallel to N because the lines perpendicular to a transversal theorem. Now, number 8, to prove parallel, I have to have some perpendicular intersections, but they have to be on the same transversal, and the two that I have are not on the same transversal. One's on S or M, one's on S or T, but they aren't shared together. So if we look back at the first theorem that we had, the first theorem said if we have some linear pairs that are congruent, they are from a set of a set of perpendicular lines. I have a linear pair with angles 1 and 2 that are congruent. That means N is perpendicular to S. And I'm going to write my little symbol in here. The reason is our linear pair perpendicular theorem. Now, I needed that so I could then say, oh, wait, I have two perpendiculars on the same transversal. So now I can say S is parallel to T because of our lines perpendicular to a transversal theorem. And the same thing, I have M and N are both perpendicular here. So if these are both perpendicular, I can then say M is parallel to N because of that same theorem, our lines perpendicular to a transversal theorem. All right, those are our notes. If you have any questions, reach out. If not, as always, we'll see you either in class or in the next video. Have a great day.